Very good morning to you all. Just waiting for a moment. How many people are we? 15. We should be all here, so that's good. Right. Let me just. Okay. Right, I've got about 10 people watching at the moment. Can you just, yeah, thanks, just announce yourself, so I've got something for the register, if you can, please, before we make a start. Okay, I've got Hayden, good morning Charlie, good morning Nick, Callum, good morning, Ryan, good morning, Ross, good morning, Declan, good morning, Brett, Shalom Brett, good day Sam, good morning Harry, Georgie, hello. Okay, some people looks like they're dropping in and out. Ryan, good morning. Good morning Amy, good morning Luke. Okay, I think we're almost all there. Let's have a look. Okay, also if somebody's watching with you, which is fine, can you just let me know that somebody's watching with you as well. Just need to have some reference. Okay, we're back up to 15. Anybody not said good morning yet? It's just I need to get the info for the register, that's all. Charlie, Corey says, well, okay, Corey, excellent. Yeah, got this. Okay, that's fine. Right, we're going to make a start. It's only going to be a short presentation. You may be pleased to hear. It's just the second part of the summary. So what I want to do is I'm not sure whether you're okay with this or you want me to go on. This afternoon I want to go back to the three-phase motor, just a quick description, and it also feeds in a little bit to what we are doing in 315 later on. Let me know if you think you're okay with this and you don't want to do it or whatever, then that's fine, okay, I won't pester you with this. But that's what I want to do this afternoon. And then the last session, as far as the 309 is concerned, is just talking you through the assessments. There are 3 different assessments. And I'll just pass them on to you. I'm not sure whether we give you time for that or not give you time, or you do it in your spare time. I have to check it with Gary. So that might keep you busy for the rest of the week as far as my sessions are concerned, if you can do this within the lecture time. Yeah. There are 3 assessments. One assessment is supposed to be done in, I think 2 of them are in 3 hours and 1 in 2 hours, and that's in your own time. Okay. Thanks, Amy. Joe's watching too. Okay, thank you. Okay, I got the info. Thanks for that. Right. Anyway, that's sort of the plan so far. We'll get to it when we are there. Right, this is the second part. So again, this just feeds directly into the assessment. Obviously, all this is going to be stored online, so you can access it later. I'm just going to talk you through a little bit, and then and that's all. That's really all. And some of the stuff, I had a look through the assessments, and I looked at some of the stuff which we talked about quite a long time ago, and I thought you would need to maybe get a little bit of a refresher. And some of the stuff I think we haven't talked about it at all. So I put this in here as well, just to make sure everything is being covered before we go to the assessment. Okay, the first one is a 3-phase boiler. We talked about it, sometimes also called a condenser boiler. And so you've got and that's, in a domestic environment, that's the boiler you would have at home. If it's a fairly recent one. Good morning, Alex. I'm just looking at the sheet here. Okay, if it's a recent boiler, most likely it would work on the same principle. So you've got a flame which goes in, you've got a burner, the flame goes in, and then you've got, okay, I'm just going to watch the mouse. The flame goes in, and then you've got the return chamber, and you've got some, almost like a heat exchanger, you've got some pipes where the hot steam goes through, and then you've got some pipes going through that as well, and you've got your water level in here. And then right at the end you've got the stack. Now the whole purpose is that that you utilize most of the energy. So by the time the steam comes out of the stack, it's actually fairly cold. It's cold steam, and I mean, you wouldn't have the chance. Maybe you have. I don't know. If you've got the flue of your condenser boiler somewhere within reach, and you put your hand on the steam of the condenser boiler, be careful. I mean, obviously, it could be hot if it's not a recent one. What you will find is that the steam is actually relatively cold. It's relatively cold, and it's quite surprising. In my house, I've got quite an old boiler, and the flue is fairly high up, so I can't do this. But I know that that the steam that comes out is quite warm or hot. At my caravan, I've got a static caravan. I've got one of these modern condenser boilers, and I can put my hand when I go outside the door. I can put my hand near the flue. And it's just like, it's almost like, I don't know, like, I wouldn't say cold, but it's sort of lukewarm, that's all. So I think the efficiency goes up to about 90%, 96%. Okay, and this instance here, I mean, this diagram is from a three-phase boiler, which is used for steam generation. So you can see this here, you've got a pressure gauge, you've got a steam stop valve and safety valve, and somewhere there would be an outlet for the steam. And you would use the steam within a factory. A question to you: I mean, do you use steam? Have you got a steam circuit where you are? I'm just trying to think. Coca-Cola is probably not necessary. Not sure about Hovis. Do you produce steam yourself, or do you have anything? Okay, I'll put this question out here for you to come back. Let me just type it as well. Okay, just going to type out the question. It's always a problem with the difference in time. So you see this about a minute after I've spoken. Okay, you've got boilers for steam. Let me just go this one. What? It's interesting. So that's at Hovis. So you generate your own steam. Provers, okay. And here's my stupid question: what are provers? Let me just type this. So anyway, one of the questions in the assignment is about steam generation and about three-phase boilers, and I mean, feel free to use this diagram if you want to, or just Google something, pick up another one, and then just write a little bit around it. And the whole reason is just efficiency. It's just a matter of efficiency. You want to get your energy utilized as high as possible, 90% or whatever. Okay, we've got some answers here. Provers add humidity to the bread to raise the dough. We do this through steam. Okay, that's interesting. I didn't know that. Hey, next we use steam, but it's a product and not for heating because we make RO water. Okay. Next question is, what is RO water? I feel I need to learn a lot here. Oh, is it our own water? Is this what you meant to say? I'm not sure whether I'm reading it right. But yeah, that's interesting. That's interesting that you use steam. Okay, I'm just waiting for the answer there. I'm gonna move on slightly at this point. I'm just looking at the answers coming through. This is the boiler, just an image of a three-phase boiler, what they look like. And again, just follow the mouse. When you go back, obviously it's just a diagram. You see all these pipes here, where the pipes go through, and where you've got, some gas or something burnt up. Okay, we've got some answers. Reverse osmosis, I think, for purifying water. Okay, thanks for that, Hayden and Amy. Okay, so anyway, we've got the water level here, and you've got the pipes here, and the water sort of goes around the pipes. When you look at the boiler, the way it's for real, you can see the pipes at the back, okay, and sort of the hot steam or the hot gas, which comes from burning it, would go through that, and you would have some water in there, which then would be turned into steam or heated water. And that's a typical boiler. I'm not sure whether whatever boiler you have for steam generation looks anything like it, but that's as big or bigger or smaller. So maybe you could comment on that briefly. And anyway, let's move on. The next area is heating fuels for production plants. So we're looking at power production, and it's just one question which comes up, and pretty much an obvious answer. So we've got electricity. Let me just rephrase it. So this is heating fuels for production plants, for heat production, no power plants, heat production. We're going to come to power plants as well, because power plants produce heat as well as a byproduct. And then sometimes it is used for heating. So you've got, buy one get one free. You generate electricity, but you get heat out of it. We're going to look at this in the next slides. In this instance, we're just looking at heating fuels for production plants. Okay, I'm just looking at the text. I'm sorry that I go to and fro a little bit. Declan says it looks very similar. That's a previous diagram. Let me just go back one moment. So that's what you've got at Hovis, a similar setup. Not sure what it's like for Coca-Cola. Anyway, electricity is can be used for heating stuff up, and that's depends where you go. It's not the most economical way of doing this. When you bear in mind the electricity has to be produced, it has to be moved from wherever it's produced to wherever you are. There are obviously little profit margins in there as well. So sometimes it's not, especially if you produce steam or heat on a great scale, it's not the cheapest way of doing this. So you might be better off to use coal or gas or oil instead, and to produce your own heat rather than having a power plant taking coal, turning it into electricity, and then the electricity is piped through to you, and then you turn it into heat. So you may as well just use the coal or the gas at the same time to start off with. The efficiency, I think, in producing heat in power plants is somewhere around 40%, 45%. And again, then when you turn electricity to heat, you've got all the losses on the way. The percentage goes right down. And so heating with electricity, instead of using coal or gas or oil, tends to be more expensive, a little bit more expensive, or quite depending on what scale it is, could be quite a lot more expensive. Steam as well, so you can use steam for heating things up, and I've got one student who works at Syngenta, and what is just going? I've got a student who works at Syngenta, and they were telling me that, or he was telling me that they have got huge, lot of pipelines which are all filled up with steam, and they're used for various production processes. So they produce their own steam. And again, it's used for heat transfer and all sorts of other stuff as well. Okay. Right, combined heat and power unit. So that's what we are looking at this, and this is a cogeneration principle where you've got a fuel, and it could be vegetable oil, bioethanol, heating oil, natural gas, coal, biomass, biogas, municipal waste. You've got a cogeneration plant. So one of them is power, electricity, and the other thing is heat, and you use this for whatever it may be needed. In the old, I don't know, in the 90s, in the old days, good old days, that was the 80s. I had the privilege to go to the GDR, and the GDR was the other side of Germany, East Germany, and I knew some people over there. It was quite interesting to get in, and that was when it was still under communism, and it was almost impossible to get in from the West. Not almost impossible, it was very difficult. You had to have a reason, an invitation. Then once you went through, they took my car apart, and through the borders between West and East, they took my car to bits, and I found things in my car which I'd lost for a long time. That was quite interesting. They took all the seats out and everything, but they did this for everyone. And anyway, I was sort of meeting up with friends or family, and one of the guys I met, he was an engineer. And he worked within within a power plant, which used the part of the water which was heated up, as part of the steam process and running the turbines. So they used part of the water, and they used it to pump this into high-rise flats. So everybody in East Germany was living in high-rise flat, pretty much everybody, and so he took me into this plant to have a look around and to see sort of how it works. And the big problem they had, and this was pretty much what he was looking after, was that the steam was under very high pressure, and you couldn't put this into a heating system within a high-rise flat. So if you've got like a huge amount of pressure, a couple of 100 bars, and anything goes wrong, it would just kill people and scald people. So they had a plant which was receiving the high pressure steam high pressure steam from the power plant. They would feed it through a massive heat exchanger, and then they would have the high pressure circuit through a heat exchanger connected through a low pressure circuit, and the low pressure circuit then in turn would feed all the residential areas in the region to pump the water up the high-rise flats, and so that was one example where both of them were used and where pretty much all the heat was used. And from the point of view, it was actually quite good. It was, economically very friendly. It was very efficient, and it worked really well. And within communism, heating was free, pretty much. Your apartments were very cheap. You didn't pay much. That was sort of their philosophy, and that's the way they worked in East Germany. When it all changed over, it was very different. You had to pay for your heat, and they had to measure it somehow, and things went very different. But anyway, it's just one example where this is being used, and where we've got combined heat and power units. Another example is where you've got a combined heat and power unit is your car. You've got your car engine, and your car engine produces motion. That's obviously the main purpose, but it's a byproduct is heat, and you need the heat for two things. Number one is you need to heat up the engine block to have better performance. So if your engine is cold, the performance is not quite as good. So it needs to heat up to about 100 degrees or something, or near enough 100 degrees, about 90 degrees, and your engine performs a lot better. So the oil, the viscosity is better, and the whole performance of the engine, everything, ignition, everything else is a lot better. So you keep it at a high temperature all the time. So you use the heat for which the engine produces anyway, for keeping the temperature of the car at a set point, about 90 odd degrees or something, and then you also use it to heat up the inside of the car, and it's just a byproduct you otherwise would have to get rid of anyway, and so it's nicely done, So it really sort of dawned on me a company, the boss for a company I used to work for, she had an electric car, a Nissan Leaf. And obviously there was no heat involved, so the engine wasn't producing any heat. And if you were driving around in winter time with that thing, you had to turn the heater on, and the heater would draw a lot of electricity from the battery, which meant that your mileage range went down. Not much, but it was noticeable. It was a few miles it went down, so you couldn't drive the thing quite as far as you could otherwise. But that was interesting as well. So heat was actually quite a problem. In summertime with that thing, it had air conditioning, and obviously the air conditioning unit would take up a lot of power as well. Okay, power plants produce electricity and use heat for domestic industrial heating, so we just talked about that. And then the next one is a steam generating plant. Steam generating plant consists of a boiler for the production of steam and other auxiliary equipment for utilization of flue gases. Okay, the heat of combustion in the boiler is utilized to convert water into steam at high temperature. It's all obvious stuff, I'm sure you know this. Okay, we're going to move on. The next one is, and we haven't covered this as part of the course, I think, and this is the rotary screw compressor. And this is about air compressors. So I'm sure that where you work, you've got a compressed air all over the place for actuators, and you probably somewhere have got a really big compressor. And that's just an example of what these compressors look like. So you've got this big tank for compressed air. You would have a pump somewhere, and there are different types of compressors. I mean, most of the compressors I've come along, they're all piston operated, so it's just like almost like a car engine where you've got a valve, a couple of valves, and they let the air in. The piston moves up and pushes the air into the compressor, and they're quite noisy and very difficult to control as far as the noise is concerned. Little anecdote here as well. My brother has got a compressor, and for just pumping up car tires and spraying, paint spraying and stuff like that. And what it does is it just builds up the pressure, and once it's built up the pressure, it just stops running, and then it gradually lowers the the thing leaks a little bit here and there. Then eventually it kicks back in again, and it builds up the pressure again. And I remember we were working on this, we were doing some stuff, and totally forgot to turn the thing off. And normally, you don't hear anything or whatever. It's just like whenever it's the pressure drops down, it starts sort of kicking in. What we found is that the thing just started kicking off in the middle of the night. So it's a residential area, and then suddenly in the middle of the night you have a right racket going on in the garage with the pressure being building up. Nobody said a word. I think it could have been quite annoying. I'm sure it was annoying for the neighbors, but nobody dared. Not sure whether they dared to say a word or they just let it go by. It wasn't happening all the time. It was just an oversight, but it can happen. This type of compressor, and that's the reason why I mentioned this with the piston and the noise and all that. This is a rotary screw for compressors. And you can see how this works. So the thing turns around, so you've got some gears, the gears turn around. Then you've got your asymmetric rotors, and they're almost like, these helical screws, which pick up the air and press out the air. I have to say, I haven't come across them, but I would imagine, not knowingly, but I would imagine that they are a lot quieter and a lot less noisy than piston-based compressors. I'm not 100% sure, but the compressor we've got in the PMC, I think, is based on pistons, so it's quite a noisy little thing to once you turn it on. So I think this compressor is quieter. It will be by default a lot quieter because you don't have the piston action, which is coming in and out. And here's a question to you. Do you know whether you've got anything like this at work? Have you ever heard about this rotary screw for compressors? And I'm just going to type it out. Just throwing this question out there. Yeah. Okay. Yeah, I'm not surprised. They're probably cheaper. I don't know, but okay. Brett, not sure about compressors. Okay. Yeah, it's like whenever I've been somewhere, you could almost hear the piston. It's just this typical piston action, and they're sort of very noisy. And as I said, like I've never come across, but I would imagine that you wouldn't have this piston noise. It would just be a whizzing noise or something. But then again, I don't know. Okay, you've got rotary screws to move the flour at some stages of the process. Okay, Georgie, thanks for that. They're all piston operated. Okay. Okay, Brett, question: how noisy are the rotary screw? For the flour pump? Just out of interest. Okay, still waiting for answers here. Moving on slightly, little bit. The next bit we're going to look at is the refrigeration process. I'm just going to go through one more time. You need to do this for the assignment as well. Okay. Right. When you look at the refrigeration process, it's fairly straightforward. Okay, Brett, I'm just going back to the comment here in the chat room. I wouldn't say too noisy. It's a noisy environment. Okay, fair enough. Thanks for that, Brett. Thanks for the feedback. Okay, going back to the refrigeration process, and again, one thing I always try to sort of illustrate this is when you use a bicycle pump. And when you get a bicycle pump and you put your thumb at the end of it and you compress air, what you find is that the air heats up. And that's pretty much the same as this works as well. So it heats up on one side. In theory, this is a theory, if you've got the old valve for bicycles, which used to be just a piece of rubber stuck on top of a hole, so it was quite hard to pump the air in. So you had quite a bit of resistance to pump it in, and then on the other side it would, be all free. So as you pump up your bicycle tires, you pump in almost hot air, but as it sort of expands again inside the tire, it should actually cool down. I don't know. I've never tested it, so I don't know whether it's true. But this would be the same process which we find for refrigerators. So we've got a compressor here, and all a compressor is just a pump. That's all it is, just a box standard pump that pumps a liquid from one side to the other. And then on the condenser side, we've got sort of a pressurized area. So the condenser will compress this liquid, which is there, or it's like a gas liquid mix at the time, so it compresses it. And as it is compressed, it loses heat. And the compression takes place because we've got the throttle valve here. If it weren't for the valve, all we had would be just a liquid moving from A to B, and nothing would really be happening. So the throttle valve pressurizes the gas liquid mixture on one side, and with the pressure that's generated. And then as the other side is there, there's going to be some sort of almost like a low pressure area. So if you've got a high pressure area on this side of the valve, if you follow the mouse, and a low pressure area on the other side of the valve where the evaporator is. So on the evaporator side, it'll cool down and it can be used for refrigeration. And on the condenser side, it actually heats up. Yeah. So and again, it's very important that we get rid of the heat to have maximum performance of our refrigerator. So one of the nightmares is, which sometimes happens if you've got a refrigerator in the kitchen or something, that it's nicely fitted into a corner and there's no ventilation taking place, and so the hot air can't go anywhere. You get like the whole thing behind the fridge heating up, and that's actually not very good for the efficiency of a fridge. So it needs to work a bit harder to try and keep the refrigeration process going. Okay, we've got the refrigeration cycle, we've got the compressor, which is basically just a pump, which is used to pressurize the refrigerant. The refrigerant, you have to imagine, is sort of a mixture of bits of gas, bits of liquid, by the time. Then we've got a condenser. Condenser removes heat from the pressurized refrigerant. So again, it's just like at the back of your fridge. If you ever take a fridge out, to clean it or whatever, put your hand on actually don't put your hand because it could be really hot, but put it near the sort of the black grid which is behind the fridge, and you will find that it's actually quite warm. And then obviously on the inside it's cold. And then we've got the throttle valve, and that sort of allows the heat to build up on one side where the refrigerant is compressed, and then the evaporator. And the evaporator is an under pressure area, so it allows the refrigerant to absorb heat from the outside. So that's what it's doing, and hence it cools down the environment, and that's what the evaporator does. Okay. Again, it's just like a very simple explanation here. So all you need to do is when you come to the write-up is just take this and embellish it a little bit. That's really all you need to do. Okay, there's a legislation on refrigerants due to the widespread use of CFCs. So that's carbon fluoride, CFCs. I think it's called. I've forgotten what the acronym stands for, but it used to be the refrigerant chemical and the chemical for everything, until they realized that the CFCs were destroying the ozone layer. We need the ozone layer to absorb UV light, and UV light, if you get UV light on our skin, it causes cancer and it'll damage life in general. So if we didn't have the ozone layer, life wouldn't be possible here on Earth. All plant life would be destroyed through UV light, high intensity UV light. So that's what they realized. When they realized that CFCs are not as good and that they are quite destructive, they all rise up to the higher atmospheres and cause a lot of damage. They then phased out CFCs, which probably a good thing. The problem with refrigerants before was that that most of them were actually explosive. So a good refrigerant, for example, is butane and propane. You could use this as a refrigerant, but the problem is that if there's a leak and somebody smokes or whatever and goes anywhere near the fridge, it'll actually start burning up. If the mixture is right. So the mixture between air and gas. So it's quite dangerous. And they were looking for something that's like a gas liquid type refrigerant type that doesn't burn up, that doesn't cause any major problems, and can be used for the refrigeration process. And I think what they're looking at now, they've got some other a derivative of this carbon fluoride, the CFCs, which got slightly different title, but they don't allegedly damage the ozone layer, and they're not toxic. That's the other one as well. Ammonia, you could use ammonia as well. Ammonia is highly toxic, so that's not a good refrigerant. And then the other ones were just flammable. So the legislation around refrigerants are that they should be captured, because we don't know whether when you get rid of a fridge, whether there's some CFCs in it or not. They're looking at other refrigerants which are quite benevolent, like CO2. They were looking at that. And again, CO2 is all over. You breathe out CO2. So once we use CO2, there wouldn't be any issue with refrigeration anymore. You could just destroy a fridge, and all you would release is the stuff you would breathe out anyway. So it's not too bad. Right, so that's the legislation. So you can't just take a fridge and say, right, just get rid of it, chuck it away. But you need to dispose of it in a legal manner through a licensed contractor, and not just chop it up and put it in a skip or something. You're not allowed to do that. Right, next one. We've got Tascam. We're almost done with the presentation, so it's about half an hour, a little bit more. That's what I thought. We've got a couple of tasks. What heating fluids are used at your place of work? In your own words, explain the refrigeration cycle. What are the issues when dealing with the refrigerants or when disposing of refrigeration units? What is the use? What is the use for steam in a plant? Let me just rephrase this. This doesn't sound right. What is steam used for in a plant? Let's change this. Right, get this right. Let's. What is steam used for in a plant? That's what it should say. Right, slideshow. View show. Just go right to the end. What is steam used for in a plant? What are the health and safety issues when dealing with steam? So have a think about it. What is a combined heat and power unit? What are the advantages? What are the advantages of a three-phase boiler? Okay, I'll leave this with you for uploading maybe to one file. I think the importance is with one file is that it's getting monitored and there needs to be some activity on one file. So I think that's why I've been told to tell you to upload your stuff on one file. Okay, I leave this up for a moment. I found out that it takes quite a few minutes for the presentation to come back up again. And then again, I can email this to you as well, can't I? So I'll email the tasks to you, and you can do them maybe for this afternoon. Okay, any questions? Are you okay with everything we did today? It's not that hard, is it, what we covered today? Any questions? That's the main thing. Let me just write this down. Right, are you okay with everything? Just some more feedback. Thanks, Brad, for getting back on that. Okay, I'm not getting anything, but it's always this delay of about a minute. Anyway, this afternoon we're gonna look at the answers for the three-phase motor. So I'm just gonna quickly go through it one more time. What I would like you to do is as well for this afternoon, just the email I've sent out yesterday evening, I think it was, so yesterday late afternoon, with the with the questions at the bottom of it, please do them and upload them to one file. If you can, email them to me as well. So I've got a rough idea of who has done what and whether you've covered it. Also, if you've got problems, feel free to email me. Then it gives me an idea of what to talk about this afternoon. Then we're going to go through this motor thing, the 3-phase motor, one more time. And if we've got time, we'll look at the first assignment you have to do. And then, as I said, like you get time allocated, and so probably by this week it should all be done. That's what we are doing. Okay, I've got some answers here. Ross, Declan, Charlie. That's okay. Thank you. Right, I'm gonna end the stream. Amy as well. It's a good question. It's all criteria, isn't it, for this bit here? Choose any. Just again, the reason is one file is monitored, so it's not just monitored by Gary, but there are other people involved as well. So that's the reason why I think people want to see that there's some activity going on one file, and that's the importance to put it on there. So it's just to prove that we are doing something, that we are not just laying in the sun and enjoying the lockdown, but that we're actually working. That's really where this whole idea comes from. Right. Okay, I'll see you this afternoon. Time's about 2:00, so I'll be on at 2:00. Again, the motor, and depending how fast we get through the whole motor thing. So it's just like the worksheet, and I've got some answers there. So I'm going to go through the worksheet one more time, do the answers, but please work your way through them before we do the session this afternoon. And then if we have time, if it's more than half an hour, I'm going to finish there. If it's less than half an hour, we're going to go through the first assignment part, and then you'll get some time to work through that. Yeah. So I'll probably meet with you tomorrow morning very briefly, and just maybe 10 minutes or whatever, and then give you time to work through that. And then the expectation is that after the 3-hour session you upload it, or you email it to me, the work you've done. Right, okay. I'll see you this afternoon, okay? So I'll end the stream now.